So, quick summary from last time. We talked about kind of discrete time dynamics stuff and basically how to simulate robots on a computer, right? You get your ODEs, do your F equals MA, use your toolbox, whatever, and then you use an integrator. RK4 is the go-to. Talk about implicit Euler and other stuff, right? We did that stuff. We talked about stability a little bit more. So we did specifically, for discrete time systems, right? More of this like linearize and check the eigenvalues kind of stuff, right? We did forward and backward Euler. And RK4, right, all that good stuff. Cool. Questions on any of that? Good. Cool. And then today, we're going to start getting into optimization, kind of do a little crash course and just more or less standard optimization topics. So the first thing we're going to talk about is a little notation. There was just a question about, and then we'll do a little chat about root finding. And then kind of get started with minimization, right? And kind of start thinking about that stuff, which will then there'll be a couple more like optimization crash course lectures. We'll give it's optimal control. First half of that is optimal, so we're gonna do that for a few days. Do a crash course in optimization, and then next week we'll like start doing controls with it. Cool. All right. So first off, these are some notes on notation. So I'm sure everybody in here is like taking a gradient before. We will have in here very strong opinions on what that means and how you should write it. So given a function f of x that is scalar valued, i.e., so this thing, it's from Rn to R, which means it eats a vector and spits out a scalar. So x is a vector in Rn, the output of the function is a scalar. And where these show up, right, is these are our cost functions in control. So think cost function. Okay, so given that function f, for us, partial f, partial x, written like that, is a row vector. So 1 by n. And this is always the case. And there's a good reason why. So this is not a column, this is a row. You might talk to other people in like statistics, machine learning, or whatever, who write gradients as column vectors. They're wrong. You can tell them they're wrong. You can tell them I said they're wrong. And this is why. So this is because ultimately what this thing is doing, it's the local, like first order linear approximation of the function f. And what we mean by that is, df dx it's like one way of saying it is the linear operator mapping little changes in x, the little delta x's, into little changes in f in the output, right? So if I were to write that out like Taylor expansion style, I'd have something like this, right? F of x plus delta x is approximately f of x plus df dx times delta x, right? It's exactly the same way we're familiar with like freshman calculus, like scalars. If I make x a vector now, for that to make any sense at all, if delta x is the same size as x, right? It's a vector in Rn. For that equation to work out dimensionally and have it spit out a scalar, df dx, for df dx to multiply a delta x be a row, right? For that like expression to make any sense, right? So that's why. Everyone cool with that? And the big reason why this is important, and I'm going to be a pain about it, is if you do it the other way, it breaks the. So if you do it this way, life is good. That all makes sense. And now I can do the chain rule, and it still works. If you do it the other way, you end up with messy, bad, buggy code with random transposes all over the place that you have to debug, and it breaks the chain rule. Okay, so we're good with that. Similarly, if I have another function g of y that is from Rm to Rn, say, so now we're talking a vector valued function of a vector, right? So y is a vector here in Rm, and then the output of the function g is also a vector, right? So the thing you should be thinking here is like a dynamics function, right? So it eats an x and a u maybe and spits out an x dot or xk plus one or something like this, right? So it's got a vector output and a vector input, right? So we all know, right, if we take this thing's derivative, we get a Jacobian matrix. Um, and so just kind of being consistent about everything, if I do this, the dimensions of this guy should be Rn by m. And that just means, the input side's got to be m dimensional. It's got to take a delta y in, and the output dimension's got to be n dimensional. Same story. We just want to be able to write g of y plus delta y is approximately g of y plus partial g partial y times delta y. And just for the dimensions to work out, it has to be n by m. Easy. Okay, so then, yeah, the kind of like the punchline of this whole thing is these conventions make the chain rule work. So in particular, if I have f of g of y plus delta y, right? Well, if I want to like compose those functions and then take the derivative of that whole thing, that's the chain rule. So I'm going to get, this is approximately f of g of y plus partial f partial x or whatever, evaluated at y, g of y, the nominal input, times partial g partial y, evaluated at y, times delta y. And that just works. I don't have to think about it. Chain rule works as usual, with the caveat like here, these things are matrices and stuff, so they don't commute. So the order matters. So you go left to right, but the chain rule works like you're used to from freshman calculus with scalars. Everyone cool with that? Okay. This is the law. This is the way it is. It's good for you. Okay, cool. So that's that. And then because it's going to be convenient, we're going to also define a couple of shorthand things. So we're going to find this guy, this like nabla f or del f of x, to be partial f partial x transpose. So that's the column version. You can write it like that with a transpose on it too if you want to. This is just for convenience. We'll define this guy. So this is R n by 1 column. And then also, similarly, we're going to define, because it shows up a lot in optimization, del squared f of x to be partial respect to x of del f of x, which is also equal to d squared f dx squared, which is the Hessian matrix, right? So that's our cost function Hessian kind of thing. We'll see that a lot. So this guy is our, maybe I should, yeah, everyone cool with that? Most people have seen this stuff before, right? I'm assuming. Show of hands, people seen Hessians, Jacobians, blah, blah, blah. Cool. Has anyone written gradients, column vectors in their lives? I'll forgive you. It's okay. Don't do it. Okay, cool. All right, everyone good with that? Yeah. No. The Hessian is an n by n matrix for a scalar valued function f. So think f is our cost function. It's got a scalar output, vector input. If it has an n-dimensional vector input, it's an n by n square matrix. The reason is it's a Taylor expansion of f. So maybe I'll make this explicit. So what's going on there is if I take a second order Taylor expansion of f, I've got f of x plus delta x is approximately f of x plus partial f partial x times delta x, plus if I go So the next term in the Taylor expansion, I've got 1/2 delta x transpose d squared f dx squared. That's the quadratic, like the second order term. That makes sense? That's why it's got to look like that. This way, it turns out it's got to be symmetric as long as your function isn't like perverse. If the function's like C2 smooth, like has a nice well-defined second derivative, this guy's a symmetric. And it's got to be fun. So this is a quadratic form. Turns out it only makes sense in quad symmetric. It turns out the symmetric part has one, cancels out. Okay. Everybody cool with this? Yeah. I mean, it's just algebra, right? So if I have like a function with two arguments, x1 and x2, say, it's like, you know, partial respect to, partial squared f respect to x1, x2, they're the mixed partials. If I take the derivative with respect to x1 and then take the derivative with respect to x2 or vice versa, that's what the off-diagonal terms are. They're just mixed partial derivatives. It's just all the second derivative, right? So this function has a bunch of inputs, and you have to take all the second derivatives of that function with respect to all the arguments. So if I have a function, if I took a vector input and rewrote it as a bunch of scalars, right? So I've got x, y, z, say, I've got to take all of the possible second derivatives. So that's d squared f dx squared, d squared f dy squared, d squared f dz squared. So that's the diagonal. And then I've also got d squared f dx dy, right? So I take the x derivative, then the y derivative. Got to take the x derivative, then z derivative, blah, blah, blah. And those are all, it's just, I'm doing all those second derivatives. And then I organize them into a matrix, right? That's what it is. That makes sense? I mean, so what the second derivative is the curvature, right? So like the first derivative is the slope, and the second derivative is the curvature. So it's local curvature. I mean, that's kind of physically what it is. In terms of a physical interpretation, it totally depends on what the function is, what that function means physically. But generally speaking, second derivatives correspond to some kind of curvature. So that can mean anything, depending on the context. For instance, second derivatives, Hessians are, in some contexts, they're mass matrices. In dynamics, the mass matrix is actually a Hessian, like second derivative, like the Lagrangian. It totally depends. Like they do have physical interpretations in many, many contexts, but totally context dependent. Depends on what your F is, physically. But it does often have a physical meaning. So the one that immediately comes to mind is mass matrix or inertia matrix is a Hessian. Is why it's got to be symmetric positive definite. Yeah, yeah. Cool. Anybody else? All right, cool. Yeah, there's lots of other physical examples, but it's, totally context dependent. Okay, guys. So we're all good with that. Next up, we're going to start talking about root finding. Who's done this before? Okay, not too many people. I guess it's a good thing we're doing this. All right, so then the idea here, first of all, what do we mean by a root of a function? This is, so given like f of x, we want to find an x star such that f of x star equals 0. So it's also known as a zero of the function, root of the function, whatever. It's a point where the function equals 0. Cool. And it can be, to be clear, f can be scalar valued or vector valued. Like in the case of a vector value function, it's where like all the outputs are 0, right? It's just a place where the function's 0. So a good example of this that we've already seen. Anyone come one we did like last couple lectures? Yeah, exactly. Equilibrium point. And this is why we're doing this stuff. It has relevance to the control stuff, right? So this is where we've seen it already is equilibrium of a continuous time system. Okay, cool. So that's a root. There's a very, very closely related concept, like almost equivalent concept, which is called a fixed point. Who's seen this? Hands? Same, about the same. Okay, cool. So, so a fixed point is where you've got f of x star equals x star. So it's a x star such that you plug it into f and you get the same thing back. Where have we seen that before? It's the equilibrium point of a discrete time dynamic, right? So continuous time dynamics, we're talking about roots, zeros, where x dot equals zero. Discrete time dynamics, the same idea is, xk plus one equals xk, right? I plug in some point and at the next time step, it's still at the same point. That makes sense? Cool. So these two things are extremely closely related. You can think of it as the continuous time and discrete time versions of an equilibrium point, right? Okay. And you can turn one into the other, right? So let's see how, like, if I have a fixed point, how do I turn that into a root finding problem? Yeah, exactly. I just move the x star over. So if I write down f of x star minus x star and make that a new function, now that's a root finding problem, right? So they're almost the same thing. And basically all the algorithms for these are the same. They're super similar, right? Okay, cool. So the first way to, like, if I give you some random f and I ask you to find a fixed point of it or a root of it, the first, like, thing you'll ever learn about, and like kind of the simplest way to do this, um, is called fixed point iteration. And it's um it's very intuitive. Like, the idea is basically, if you give me some f, think about dynamics, right? If I have a system that has a stable equilibrium point, so think about like a damped oscillator, like think about a pendulum with damping. If I just simulate it forward, what's it going to do? It's going to just like naturally settle into that equilibrium point, right? So fixed point iteration literally just means make a guess, and just run the f a bunch, iterate the f a bunch, i.e., simulate the dynamics a bunch until it settles into x. It's going to settle into a fixed point as long as the fixed point's stable, right? So it's like basically kind of trivial, and but it only works. So let me write that down. If the fixed point is stable, um, cool. So this the caveat is, right, this only works for stable X star. So it would work for the, like on the pendulum, it would work for this one, but not this one, right? Um, and the other problem is it actually has very slow convergence. Like you're gonna have to like run this thing a lot of time steps, right? So not the awesomest. Okay, so let's take a look at this. As long as I can get my, it's like, so yeah, basically the idea is you make an initial guess and then you run it, right? So what do you think is going to happen? It's just going to go to the one that's closest to where you start, essentially. So like there's a related concept here called basin of attraction. You can imagine, we'll talk more about this, but imagine, so you're talking about like some function that has some landscape of like minima and whatever. And basically, let's say I have like something that looks like this. If I start over here, it's going to go to this one. If I start over here somewhere, it's going to probably go to this one, that kind of thing. It's like, think about ball rolling down a hill, that sort of vibe, right? So every one of these fixed points has a basin of attraction where if you start somewhere in that basin, it's going to end up at that fixed point. And there might be, if you have multiple equilibria, there's going to be multiple basins of attraction, right? This seems straightforward, and it kind of is for the most part. It's surprisingly complicated, though, it turns out. If you actually, there's relatively trivial functions you can write down with multiple fixed points where it, in the neighborhood of the basin, the equilibrium point, it makes sense. It does what you expect, but actually the boundaries of these basins where you transition from one basin to the other can actually be chaotic, which is insane. So like basically you get these, if you imagine you had multiple, the boundary between the two basins can have this insanely complicated like fractal pattern where, because you can think of it's like a knife edge, you can do it one way or the other kind of thing. But so the neighborhood of that transition zone can be insane. No, no, no. I mean, it's sort of it's actually like given this like chaotic thing I'm telling you about, it's very crazy. It can be like so it's sort of what you expect if you're like in the basin, but then the boundaries between the basins can be just gross and really weird. What was I going to do? I was going to show you code. Let's go. Okay, so here's some stuff. Let's just kind of run through this real quick and show you this. Maybe we'll wait on this. So here's backward Euler. This is what we did last time. So this is me doing backward Euler with a fixed point iteration. So I'm basically just like uh, iterating the dynamics, if you like. I'm just doing, x k plus 1 equals like whatever, f of x kind of thing. I've moved everything over to one side. And I'm just going to run that until I get to some error tolerance that I like, right? Actually, I'm going to hold off on this because I'll do them both together. We'll do the next one, then we'll do them both. So, okay, so that's fixed point iteration. It has some downsides, right? Let's do, so the canonical way to do this, that is kind of the right thing to do in general, is Newton's method. Who's done this before? I hope most people. Cool. Okay, so the gist of this one is you're gonna fit a linear approximation to f. So we do our Taylor expansion like we just saw, x plus delta x, and you get this sort of thing. And we just set the Taylor approximation equal to 0 and solve for delta x, and then take a step using that delta x, right? So this looks like do that. Then I just like move stuff around and I get delta x equals minus partial f partial x inverse times f of x. If I do that, then I apply this correction step and I get, x, yeah, it's x plus delta x. And then I just repeat this until it converges. So, well, let's do the code now. So any questions about that? Pretty straightforward idea. It is in theory straightforward. And I should say this is like the benchmark thing to do. This is like kind of the gold standard thing for like nonlinear root finding stuff. And it works great, but there's always issues. Okay, so we talked about the fixed point thing. That's what we saw last time when we did backward Euler, and I'm solving with fixed point iteration. Turns out in this case it is stable, right? We talked about backward damping and blah blah blah. It's sort of stable. So that kind of all checks out. Here it is done with Newton. Let's just walk through this, right? So I'm going to take an Euler step as an initial guess for xk plus 1. I'm going to use xk. Just going to initialize it with the current state. This R here, it's R for residual. Yeah. Oh, yeah, yeah. Let's try. That's sort of annoying. Let's, is there a nice way to do this that makes the font bigger? I don't know. Jupyter, does it have a convenient? I can do this, but that sort of looks, that's fine. Is that good? Yeah, let's try that. Better? Yeah, I like that better. Is that cool? More? Is that good? Okay, sweet. Okay, so here's the fixed point. Yeah, here's Newton, right? So what I make up this residual function, which is turning the fixed point into a root finding, right? So I just take it's xk plus one, or I'm calling it fn, it's not here. I just subtract the other side, so I get it to be stuff equals zero. I have a root finding problem now that I can apply Newton's method to. And the idea here is I take that root finding thing that's supposed to be zero, and I compute it, and whatever is not zero, I call the residual. So that's what the R means. And the residual is the thing I'm trying to drive to zero with Newton's method. So that's what I'm trying to drive to zero. I'm going to keep track of the error at each iteration because we're going to plot this later and take a look. And then here's the loop. So I'm getting the Jacobian using forward diff, which I think was on your homework zero. This is awesome and magical. It's auto diff. It's built into Julia, so you never have to like handwrite derivatives, which is amazing. So we're going to use this because I'm lazy and I'm not going to handwrite this stuff. Um, and you're always welcome to use this in class. It also will do Hessians, blah, blah, blah. Okay, so I use this to get my Jacobian. Then this is literally what we just wrote down, right? It's the Newton step. So I do Jacobian inverse times the residual. That's my update thing. Then I compute the residual again, and then I repeat, right? I just loop that. So other kind of code notes, notice I'm using this backslash notation for Jacobian inverse. You should always do this instead of calling inv. This is numerically, so you never really want to compute a matrix inverse explicitly. What this is doing is very smart, fancy things under the hood with like matrix factorizations and back solves and stuff. So you don't have to understand the details, just know you shouldn't really ever call inv explicitly and then multiply. Just do backslash whenever you want that. So if you've used MATLAB before, same thing. Okay, so that's Newton. Everyone cool with that? Questions or anything? Okay, so we'll do that. Then I'm just going to run these guys for like a handful of time steps, and we're going to do the sim. So I'll run them both for a few time steps. That's right here. There's the same initial conditions as last time. I'm just going to run them both for like a few seconds or whatever. How many seconds? Yeah, so 10 seconds with like 100 hertz time steps, basically like we did last time. Those are the trajectories. They match, which they should. They're both solving the same equation, right? So like the same tolerance. So they give me the same simulation output. What we're going to do now, though, is go look at, so I guess we'll compare the two solutions that we got and make sure they match. And they basically, yeah, they match like, 1e minus 5 or 6 tolerances, which is cool. If I wanted to, I could put tighter error tolerances in here in the fixed point iteration. It turns out, though, we'll take a look. So, okay, so they match. They give me the same answer. Let's now look, though, at the iteration, the individual error iterations, the errors as it tries to converge with both fixed point and Newton, and look what happens. So this is fixed point iteration. You can see it's taking like 14 iterations to get down to like 1e minus 8 type of tolerances. And then let's look at, for Newton, like 3 steps. And look, like Newton is getting down to 1e minus 15. That's machine precision. That's the limit of floating point, double precision floating point on your computer. So that is 0 as far as your computer is concerned. It can't get any more accurate. Fixed point only got to like, 1e minus 8. And it took 14 iterations to get there. The obvious conclusion here is that Newton's kind of awesome and fixed point iteration's kind of bad. We talked about all these caveats. So here's the deal, right? This thing, like, so this is the Newton line. It just slams down to like full precision, like effectively 0 in like 3 steps. And then the fixed point thing, kind of like wiggles around a bunch and like kind of gets close-ish. But the takeaway here is that Newton's method has what's called quadratic convergence. Means it converges quadratically. Like roughly speaking, what that means is the number of significant digits of accuracy in your answer basically doubles every iteration. So if you've got the accuracy to like 2 significant digits, the next iteration will be 4, then 8, then 16, and then you're done. Whereas fixed point iterations converges linearly. So it's like, kind of adding a significant digit every time, maybe, or something like that. So it's way, way more iterations. Practically speaking, with Newton's method, you can like get the real answer in double precision. You can get the answer to like as accurate as your computer can go in a handful of iterations like this. So you'll get the real answer. Fixed point iteration, you can kind of get a few significant digits, but it's going to kind of stall out and take forever, and you'll never really get all the way there. So you can get like a handful of digits, but you're not going to get like the exact answer. What else is there to say about this? Why might I not do Newton? Maybe a related question. What's the most expensive part of the Newton thing? Yeah. Well, what part of it? There's compute in both. Yeah, so I'm asking like one versus the other. Yeah. Yeah. So taking that matrix inverse or more accurately solving that linear system, I'm solving this like big matrix equation in principle. So doing like 1D, 2D, 10D, no big deal. I'm solving like a 10-dimensional linear system, like whatever, 10 by 10 matrix, fine. But if we go to like a million dimensional problem, which shows up in control, like some of the stuff we're going to do, if you have like a big humanoid robot and a bunch of time steps, you can get to like hundreds of thousands or millions of dimensions pretty easily. Inverting a million by million matrix, maybe not so great, right? So that gets pretty gnarly. And in terms of big O kind of, flop count kind of stuff, Newton's method naively for like if we're not using any tricks, it's solving a linear system is n order n cubed. So if the dimension of x is n, the Newton step is n cubed flops. So as n gets bigger, it gets cubically more expensive to do Newton, whereas the fixed point iteration is just order n. So if you're a million dimensions, then it's order a million to do a fixed point iteration, but it's order a million cubed. It's really, really big and probably intractable to do a Newton step. So that is why. If it's a small system, basically Newton every time. Um, if it's a medium to big system, you have to be a little smart to use Newton, but you can probably still do it. And if it's a large system, then you're probably stuck with something first order like the fixed point stuff that we talked about. All right, so let's write that down. And then, yeah, any questions about any of this while I'm writing and stuff? So we're solving a root finding problem, but we want f of x to equal 0, right? The residual is just whatever remainder thing over there is not 0. So I want to drive the thing to 0. I want to drive the residual to 0, right? So it's whatever is left. If it's non-zero, that's the residual. It's the thing you're trying to drive to 0 in the root finding problem. We did the backward Euler thing again. And basically take away very fast convergence with Newton. Um, and then sort of um, quadratic. What else is there to say? You can get to machine precision with Newton. You can basically get the exact answer, right? Um, the most expensive part is solving a linear system in Newton's method, which is order n cubed. Um, so that sounds bad, like if you have a million dimensional problem, but we still use Newton's method on really big problems, in particular in control. And we don't have to pay n cubed to do it. It's kind of the trick. And that's where this gets really kind of interesting. And there's fancy stuff. And the gist is, especially in control, the Hessian matrix that the Jacobian that you're inverting is not dense. It's often sparse, meaning it's mostly zeros and it has a lot of structure, like it's got band patterns and stuff like this. And if you're clever and you exploit that sparsity structure, you can do this in way less than a cube. That's sort of the trick. And we're going to definitely do more of that here. And that's sort of how we can scale these to bigger problems. And generically, we talk about problem structure. But yeah, mostly what that means is that the matrix is sparse and it has specific patterns in the non-zeros. We'll that later. Okay, cool. Any questions about root finding Newton? Yeah. Yes. It can be anything. This was neither linear nor quadratic, right? This is something random This is this is like the nonlinear pendulum dynamics run through backward Euler, which has like trig in it and weird crap. Like it's definitely not any of those things. It's just nonlinear. So yeah, this works on any generic nonlinear f of x. There's no assumptions about anything. No, the complexity comes from how hard it is to invert that matrix. It's just the cost of matrix inversion, basically, like solving a linear system is n cubed. That's where it comes from. That is the most expensive part. That's like the thing that dominates the compute, and that's kind of it. Yeah, cool. Anybody else? Okay, cool. Yeah. Well, yeah. Ask me the question. Are you asking me if you can ask me a question? Yeah. Which part? Here? Newton thing? Hmm. More? Yeah. Yeah, it's this. This is the Newton step. And then I check the residual again. So the code will get posted. So you should try this. Yeah, in general, you guys should like try these Jupyter notebooks and play around, and do weird stuff with them, and experiment. And then yeah, ask questions if you after you try it and stuff. Okay, cool. All right, so let's keep on trucking then. So now we're gonna like start talking about optimization kind of properly. So we're gonna specifically talk about minimization in here. This is like again one of the big divides between RL and control. In control, we minimize costs, and in RL, you maximize rewards. The same thing, you just slap a minus sign on your function and can maximize this. There's no real difference. This is just a convention. So we're going to talk about stuff like this. We're going to minimize some f of x, where f is from Rn to R. So each vector spits out a scalar, right? And that's think cost function. Um, and so the idea here that we're going to leverage is if f is smooth, i.e., we can take its derivative. And in here, we're generally going to smooth everything smooth with some exceptions later. Um, so df dx, i.e., the gradient, is going to be 0 at a local minimum. So everyone's seen this before, right? High school calculus. Like at the bottom, it's got a flat spot. Cool. And so what we're going to do now is like literally what I just wrote there, df dx equals 0. That's a root finding problem. Some function of x equals 0, right? So I'm going to take that and now just use Newton on it. So we got this, right? Grad f equals 0, which is exactly what we just did. It's just a particular choice of function to do root finding on, right? So we're going to do Newton. And so specifically what we're going to do, let's just write that out. So we'll write out the Newton step on this guy. Looks like this. We approximate it with a Taylor expansion. So I get this guy plus partial f, or sorry, partial respect to x of this guy times delta x. We set this equal to 0. But what's this? That's the Hessian, right? So this thing is equal to del squared f, right? Okay, and then we just do what we've been doing. No difference. Um, so we solve for delta x. state X. So no surprises. And then we like repeat this until convergence, right? Okay, so, and just to like give some intuition here, like think through it a little bit, the gist of what this is doing is we're fitting a quadratic approximation to f at the point x, right? So in particular, right, I wrote that second order Taylor expansion thing out when we talked about Hessians. So this is that, right? So think about it as I have some weird nonlinear. I'm going to take a second order Taylor expansion, which is giving me a quadratic function. There's a local quadratic approximation, so a local bowl, that's approximating that function near the point. And then I'm going to exactly solve that. So I'm going to approximate with a quadratic bowl, find the minimum of that quadratic bowl, because I can do that in closed form. And then I'm going to go there. And then I'm going to do that again over and over again, right? So that's the gist. And there's lots of generalizations of Newton's method, by the way. So this, we're finding that quadratic bowl approximation using a second order Taylor expansion. But you can come up with lots of other ways to fit a quadratic bowl approximation. You could use sample points. You can do all kinds of stuff. There's many, many generalizations of this Newton idea that just use a different method for coming up with the quadratic bowl approximation. These are all called quasi-Newton methods, right? There's tons of them. But that's like, at the end of the day, that's what you want to do. You want to come up with some local quadratic bowl that approximates the function. And then that we know how to solve exactly. Okay. Uh, okay. And like one thing I'm really trying to make clear here is Newton's method is a root finding method. We can use it to do optimization or minimization, but it's not exactly an optimization algorithm. It's a root finding algorithm. But we use it for optimization when we apply it to rad equals 0, right? Okay, so let's try this out a little bit. This will be fun. So another one of these Jupyter notebooks will all be posted. Another fun little thing to mention is that there's this whole thing about Julia versions. It was a little bit on Piazza about it. In the class, we kind of had a chat with the TAs and stuff. We've decided to stick with the long-term support version of Julia, or like 1.6.7. There's a newer, release is 1.10. We're going to use LTS in here just because it's easier and should have less compatibility issues. So all these will be for 1.6. You can run it in the newer version if you want, but for homework, turning in code and stuff, let's stick with the LTS release. Okay, so we're going to just make up some stupid function here that I came up with out of nowhere. Like, some fourth order polynomial, totally made up. Because, I was less lazy this time and it's a scalar function and easy to diff, I wrote the gradient and Hessian out by hand for those guys. You can also use forward diff for this. This one was easy, so I just did it. Let's go plot this guy. Okay, so nice little wiggly function, whatever. And in particular, it's got two local minima. And presumably each one of those has a basin of attraction, right? Like I make a guess based on where I am, it's going to go to one or the other. So here's my Newton step, which we just talked about, right? Same stuff, no surprises. And now what I'm going to do is let's start this. So we'll start it at 1. So we'll start it over here as our initial guess. Run Newton. So there it is. Let's take a Newton step and see what happens. So I'm going to plot each step. We take one step. We're down here. Pretty good. Take another step. At this point, I'm like pretty much there. Take one more. That's 3 steps. I barely moved. If I do it again, I'm not going to move. So basically 3 steps and I got the answer. Cool. So pretty awesome. Works great. That's what you think. Let's try now. Let's start over here somewhere. So maybe like -1.5. And so like, what do we think is going to happen? That's too close to the answer. Let's go over a little, like 1.3 or something. Okay, so yeah, start over there. What do we think is going to happen? Where's it going to go? It's going to go to that other like local optima, right? That other dip. So let's try that, like probably. So okay, 1 step, 2 steps, 3 steps. We've got the answer, right? Sweet. Okay, let's try Another random spot. Let's try. That was cool. We started over here. We went here. Let's try somewhere over here. Let me try like 0. Okay, cool. So where do we think is going to happen now? Probably going to go to the right. Let's try it. So let's take a step. What happened? Ooh, what's going to happen? So let me run this a couple more times. Where's it ending up? Yeah, you got it. So what is this thing doing? It's finding grad equals 0. It doesn't actually know anything about whether that grad equals 0 is a max or a min, or in Mendy, a saddle point. So what this is going to do is just find you the closest fixed point, the closest place where the grad equals 0. It doesn't care if it's a min or a max. So this is going back to the point I was making before, right? Newton's method is a root finding method. We're applying it to grad equals 0, which is a necessary condition for some kind of local fixed point. Doesn't care if it's a max or min. So this is really important. Okay, so that was mostly what I want to get out of this. This is maybe not what you expected, but yeah, it's going to go towards the closest flat spot. So in this case, the closest flat spot was that guy, right? Okay, cool. So let's go do some more math and talk about that for a sec. Yeah, yeah, yes, you can, and that's going to happen in a sec. We'll talk about that. You absolutely can overshoot. Uh, this is a slightly different problem, though. Yeah, it's going to find you the closest fixed point. So when I said quadratic, I was giving you this bowl. It can also be one of these, which is what happened here, right? So it's using like a local second order approximation. It's just going for the fixed point. So it's either going to find you the bottom of a bowl or the peak of a hill. And it doesn't care as we wrote it down. It just cares about the flat spot. I was like kind of messing with you a little bit when I gave you that initial thing. Yeah, because what it's doing, right, is it's taking a local Taylor expansion at the point you're at. That's approximating the function in some like small neighborhood where you, so it's going to go towards the closest flat spot. So if you're, because of the Taylor expansion, basically, because that's a local thing, right? So at that point, when I Taylor expanded, what I got was effectively one of these. If I, well, it's again, it's a local method. All it knows about is the local first and second derivative at the point you're at. And that's what it's minimizing or finding a fixed point of, right? So whatever's closest is where it's going to go. That's all it knows. In general, global optimization is bad and hard and terrible. So like at, almost all optimization methods are like inherently local. They're getting some local picture of the landscape where you are right now, and they're using that to take a step. Gradient descent uses just the local gradient. This uses the local gradient and curvature to build a quadratic approximation, which is a better approximation, which is why it converges faster. But like everything's like kind of this local approximation kind of deal. There are situations where the local answer is the global answer, which we'll talk about in a minute. But generally speaking, global optimization, global nonlinear optimization is like empty, hard, terrible. All you can do is local stuff. I don't know if that life is bad in this case. Is like, I'm sorry to tell you, life is hard. You know, I don't know if that was answering your question or not. Okay. I mean, I'm going to write some stuff. If you have more, keep going. I'm just going to write down. This is the example we did. Um, and um, we started at like 1 minus 1.3 and then 0. And this one maximized instead of minimized, right? So why that happened and like, what are we going to do about it? Yeah. Okay, so Newton is a local emphasis root finding emphasis. That's it. Um, it will converge. Uh, so like basically the closest fixed point. And in general, to the initial guess, and it doesn't really care if it's a min, a max, or a saddle, as we initially formulate it, right? Because it's just grad equals zero. So that's another way of saying this is that grad equals zero thing is a necessary condition for a local minimum. It is not a sufficient condition, right? Because it could be any of those things, right? So now we're going to talk about sort of how to fix this and kind of what's going on. So we're going to talk about, yeah. Yeah, yeah. So we're going to talk about it right now, actually. Good insight. Okay, so we're going to talk about sufficient conditions because right now we're talking about minimizing. We want to minimize. That's convention, whatever. So far we talked about, grad f equals zero. This is these are called the first order necessary conditions for a minimum. It is not a sufficient condition. And that we need something else. And the way to get at this is let's again look at the scalar case. So that Newton step, like we're gonna like zoom in and interpret this a little bit. So think scalars, and it's just del squared f inverse times grad f. So if I think about this from like a gradient descent type of perspective, right? Like, and people have seen that before. Hands for gradient descent. Everyone's seen gradient descent pretty much. Yeah, awesome. Okay, cool. So think about this like gradient descent. So what's going on here? This is my gradient, right? And this thing, it has a minus sign out front. So that implies descent, right? Go in the opposite direction of the gradient. And then, so what's this guy thing? Like this Hessian inverse thing in here. This is basically like my learning rate or my step size if I'm thinking gradient descent. So, so thinking about it that way, think about it like a learning rate. That only works. That's only like going to take a gradient descent step if del squared f is positive. If del squared f goes negative, it's going to flip the sign and it's going to put me in the gradient ascent direction and push me uphill, right? So let's write that down. Del squared f positive implies descent or minimization. Del squared f negative implies ascent or maximization. And um, some more notes, right? So basically we have the necessary condition, which is grad f equals zero at a minimum. And then the sufficient condition is that at that point, the Hessian has to be positive. And if you have both of those, the positive means the curvature is positive, right? It's curving up. So then it has to be a minimum. So that's necessary and sufficient. That's what you need. And in the algorithm, that's kind of what's going on, right? In Newton's method. So in Rn, if we're in vector land now, not scalar, uh, same idea. What do you think we do? So now instead of scalar, that's a matrix, the Hessian matrix. So as we've been doing before, how do we like translate this into matrix land? Exactly, eigenvalues. So just like when we did this for stability stuff, we need um, the Hessian to be what's called positive definite. and you in fact overload notation same that same notation. Um, it's a sometimes it's a like a curly version of the greater than symbol, and in LaTeX it's SUCC for that guy. It's like a curly whatever. But yeah, it's positive definite. That means all the eigenvalues have to be positive. And another way that you'll see that written is this guy is in Sn plus plus. So S means symmetric matrix, N means n by n, and then the plus plus means strictly positive definite. One plus means positive semi-definite. This is notation for you for fun fact, whatever. And yeah, said out loud, this is positive definite. This gives you descent. And also, is the sufficient condition for a local minimum. Okay, so that's that. Yeah, this guy. So it's a big F. Oh, this is it's a little backwards. Yeah, it's I'll try to write it better. It's literally in. It's the math symbol for in. It looks like this. Here, I'll write it better. In LaTeX, it's backslash in. All right, yeah. Yeah, so S means symmetric matrix, N is N by N, plus plus is strictly positive definite. One plus means positive semi-definite, which means eigenvalues greater than or equal to zero, so you can have some zero eigenvalues. Plus plus means strictly positive, so have to be greater than zero. No zeros allowed. Cool. So if you had zero eigenvalues in the Hessian, what would that correspond to physically? So all positives means it's got to be a bowl. If you have one eigenvalue and eigenvector that's zero in there, what does that mean? It means you've got a valley. You've got like some eigenvector direction where it's flat at the bottom. So what that would mean is you don't have a unique minimum. It means you've got like a line of minimum, right? Or if it's got multiple zero eigenvalues, then you have a subspace where it's flat. So you might have like a couple dimensions in which it's flat locally. Yeah. Depends on the situation. Can be good, can be bad. But that's what it locally, right? It means you've got some kind of valley situation without an isolated minimum point. Okay, and so along these lines, right, worth talking about is if del squared f of x is positive definite everywhere, and if I were being fancy, I would write like this for all x, right? This is the word for that is strongly convex. This says f of x is strongly convex. What that means is that you can always solve it with Newton's method, and that if you get a solution with Newton's method, i.e. you find a local minimum with Newton's method, that is the global minimum, which is awesome, which is why convex optimization is a thing. So like to first order, roughly speaking, convex F, you can always use Newton's method and you'll always find the global optimum. That's awesome. We like that. That's why we like convex optimization. Yeah. It means it's one big bowl with only one minimum. Yeah. Yep. No, it doesn't mean in one step. If it was a quadratic function, then yes, because Newton's fitting a quadratic approximation. So if it's a quadratic function, then that's one step and done. And yeah, this is coming on the next homework, by the way. But if it's you can have something that's not quadratic, but is strongly convex. So you can imagine it can wiggle a bunch and be weird, but it has to always curve up. That's the only, right? So if it's always curving up, basically it can't have any other flat spots is the idea, right? And that's strongly convex. Then Newton's method is like guaranteed to give you the answer. That's kind of the gist. Okay. And life is good. Okay, cool. So, and then, yeah, convex optimization, life is nice. Unfortunately, life is hard, right? And so usually not true for for like hard nonlinear problems. Okay, cool. So that's that conversation. I'll go with that. So the last thing we got to do today is to talk about how to fix it when your Hessian is not positive definite so that you still descend because we want a minimum. So we're going to fix it, and then we're going to go back and show you the code. And so the magic solution to this is called regularization. And it's basically a hack, but you can sort of theoretically, kind of justify and put it on rigorous footing. Okay, so here's what you do. Select the practical solution to make sure we're always minimizing. Yeah, that's bad. Sorry. My handwriting is not good normally, and when I try to go fast, it's like just absolutely terrible. Okay, so we've got we'll do the following things. We'll compute the Hessian, we'll call it H, and then we're basically gonna just have a while loop and do sort of the following thing. So while H is not positive definite, and I'm going to write some weird symbols here, I guess, in general. They're all like legit math symbols that you can have in LaTeX, but if you're unfamiliar with some of these things, give me a shout and I will clarify. This is like, the greater than thing with a slash through it, which means not positive definite. Um, then what we're going to do is basically add the Hessian with a multiple of the identity. So that beta there is just some positive scalar. And there's sort of heuristics for choosing this. But there's no basically, there's no no magic to it. So you're going to do that. So you're going to compute your Hessian. You're going to check that's positive definite. If it's not, you're going to add some multiple of the identity to it and check again. You're just going to keep doing that until it passes the check. And then once you've passed the test and you've gotten something that's positive definite, you're then going to take your Newton step. So then you're going to do your delta x. Sorry, we'll do delta x equals minus h inverse grad f. And then, x gets the usual thing. Cool. Makes sense? Yeah. Oh, that's a left arrow, which is yes in my LaTeX and stuff. It just means I'm setting the value back equal to h and 0 there. That is not positive definite. One more line above. H gets del squared f. So left arrow. Yeah, yeah. It means you're setting the variable equal to the thing on the right, right? Okay, cool. Uh, Sorry. Yeah, this should be rad f. That what you were after? Yeah, sorry about that. Okay, all good? Yeah, definitely let me know if I screw up. I do it a lot. Okay, so this thing, it works. It guarantees a descent step. This is also called um, damped Newton when we do this. So, and there's, I guess, some interpretation when you think about this, like padding the Hessian thing as damping, because what it's doing, it's simultaneously like making it positive definite. It's also shrinking the step size, it turns out, because that thing is equivalent to adding a penalty on delta x. So having beta I in there, if I think about the quadratic cost function, right? It's 1/2 delta x transpose h delta x, right? In the Taylor expansion thing we talked about. If I add an extra beta I in there, it's like having an extra cost term that's like beta times delta x transpose delta x. So it's basically putting a penalty on that delta x step size, which in this case, where the Hessian's weird, not quite sure what's up, is not a bad thing to do. It's basically making the step more conservative. Make sense? So it's kind of doing both things. It's padding your Hessian, it's making the delta x smaller. Another way to think about this is it's actually making, so there's a Newton step that's going in this Newton direction. And there's also the gradient step that's going in the gradient negative gradient direction. When I pad the Hessian like this, it's making the step smaller. It's also rotating delta x towards the gradient direction. In the limit of a really big beta, it's basically swamping the Hessian with that identity term. And then that second order term in the Taylor expansion basically drops out and it's just the gradient term. That makes sense, right? So if I make beta really big, basically just a big identity matrix, right? Big scalar times the identity, in which case the Hessian's not doing anything. And it's just, you're just getting the gradient descent step, right? Which just has to be a descent step, right? That makes sense. So that's a little interpretation. Okay. Maybe this needs some, oh, so I'll write these things down. So this guarantees a descent step and it shrinks the step size. And it rotates you towards the gradient direction also. These are all kind of ways to think about this, ways to interpret it. So let's go do it. So here's our thing. We started at 0. Now I'm going to let's actually look at the Hessian at that point. This was that initial guess point where I started at 0. Sure enough, the Hessian's negative. So that means I've got one of these instead of one of these, and I went to the peak, right? So that makes sense, checks out. So here's what I just wrote down, regularized Newton step or damp Newton step. Same deal. I did exactly here. I check, I set H to the Hessian. I check if it's positive definite. I pad it. I set beta to 1 arbitrarily, whatever. And then I take my step. Straightforward. Cool. So let's do it. So I'll do the exact same thing. Start it at that 0 point here where before I went up. Now we're going to run this regularized Newton step and see what happens. So with the regularization in there, sure enough, I went to the right. I overshot the minimum, but I went to the right. And now we've already started over there before and we know what happens, right? So now if I take some steps, I'm going to go where I want, right? So that's like kind of 3-4 steps. Same story as before, we're good. Cool. So you had asked about overshooting before. We don't like overshooting for sure. We're going to talk about how to fix that next time. So right now we've got Newton. We've talked about it can minimize or maximize or whatever, which is not so great. So if we want to minimize, we need to look at the Hessian and be careful, pad that Hessian, called regularization or damping. Yeah. It's exactly the same. It's not similar. You could do that, yeah. So that is one strategy for making sure you don't overshoot. What you just described is basically what's called a trust region method. We'll talk about this next time. So trust region is one idea where basically what you're doing is just saying, I don't want to take a step bigger than some like radius or something like that. And you get at that effectively by tuning the beta. The other way to go is what's called a line search, which is what we're going to talk about next time. So stay tuned. So basically, yeah, there's a couple problems. You got your Hessian, I don't want to maximize problem. And then you got this overshoot problem. So the solution to the don't maximize problem is regularization or damping. We pad the Hessian to make sure it's positive definite, which makes sure we descend. The solution to the overshoot problem is a line search is what we're going to do. You can also do a trust region idea. Yeah. It's totally arbitrary. So all you need for the math to work out is for H to be strictly positive definite. So it's whatever beta needs to be to get all the eigenvalues positive. So what it actually has to be is just, it has to be bigger than the most negative eigenvalue in H. It has to be at least bigger than that. That's the only thing that it has to be. So you might think about taking like H and just take an eigendecomposition and just figure out what that most negative eigenvalue is and take that and add some epsilon to it and whatever. That's a tempting thing to do. Why wouldn't we do that? Goes back to this whole talk we had about what if it's a million dimensional problem? If H is a million by a million, I do not want to take an eigendecomposition of H. That would be a terrible thing to do. And it would be, so basically taking that eigendecomposition is more expensive than taking the Newton step. So it's a terrible idea. And so what we do in practice is there's ways to cheat to check if something's positive definite or not. So we talked about H is symmetric matrix. So for symmetric matrix, when you solve that linear system, when I do backslash, this is like fun fact at this point, it's not like stuff you're going to get. The way to actually do that, what's happening under the hood inside backslash is it's computing a Cholesky factorization. Who's seen Cholesky before? some of you guys, right? So turns out Cholesky factorization inside there, it has to divide by sort of diagonal elements and stuff. Turns out for a matrix that isn't strictly positive definite, Cholesky will fail. Basically, it'll fail whenever because it'll have a divide by zero error, divide by some weird thing. You'll end up with a divide by zero or an imaginary number somewhere in the algorithm in Cholesky. So essentially, the way this is pos-def type thing works is you just try doing Cholesky. You just try factorizing the matrix. And then if Cholesky barfs because it shows up with a divide by zero or an imaginary number, then you know it's not positive definite and you go pat it and keep moving. So there's basically cheap ways to check this in practice that work, that scale to big, that basically don't add any overhead. So to do this in general, to compute your Newton step, you're basically always doing a Cholesky. So you basically figure out there's clever ways to basically do a partial Cholesky and just stop if you run into trouble. And then you know, and keep going. That's the basically, yeah, you got to be clever when you're dealing with big problems. And you don't want to do an I opposition. I don't think anyone actually asked that, but you should know that. So there you go. Anybody else?
Hi, Zach.
Okay, so let's just kind of then like summarize this whole story. Uh, is way more expensive than doing straight up gradient descent, but it gets you the right answer to full machine precision, which gradient descent like can't do. So this thing will get you the answer in like 4 iterations. Gradient descent, you'll sit there all day and take gradient descents and you'll wiggle around the bottom and never quite get all the way there. So this is the same story as the fixed point iteration. So I should have said this more clearly, maybe. Gradient descent. So we did Newton on grad f equals 0. So we turn grad f in, we have like this minimization problem. We know grad f equals 0 is the first order necessary conditions. That's a fixed point, right? So we can do Newton on the root finding problem, fixed point. What is gradient descent? It no, it is exactly fixed point iteration. Gradient descent is fixed point iteration on grad f equals 0. It turns out. Maybe this is not obvious. So yeah, so to be precise, there's some like details I've glossed over. This is too much for right now. We can talk about this, but basically there's this idea called gradient flow. So grad f, you can think about that as dynamics, as a dynamic function. And if I were to like simulate those dynamics, if I turned grad f into like an ODE, thought about it as like a dynamics, which you can, I would get some smooth ODE, which is the path I would trace out if I just followed the gradient all the way down. If I treated the gradient as like a vector field, like a dynamics function, right? I could literally take grad f and like treat it as a dynamics model and nonlinear dynamics and integrate it with like RK4. And if I did that, I would wiggle around and whatever. That's called the gradient flow, right? So taking that into consideration, gradient descent, where I take negative whatever, that's actually forward Euler integration on the gradient flow. This is all very trippy, weird stuff that isn't like for general consumption. We can maybe take this offline. So gradient descent is Euler integration on the gradient flow, and like uh, uh, gradient descent is also a fixed point iteration on that, right? So if I have this gradient flow ODE idea, if I do forward Euler on it, I get a discrete time thing, and that's actually what gradient descent algorithm is, where this learning rate or time step is your time step for your Euler integration. Now I have a discrete time system, and it's a fixed point of the discrete time system. And if I do fixed point iteration on that, that's it. So it's all the same thing. And basically the fixed point sort of sucking compared to Newton argument is the same thing. If the gradient descent equals fixed point iteration, I really need to like revamp this and like maybe there's too much in there to like explain in an hour. So I'm like, there's more detail. If you want more of this content, come talk to me. I will talk at you all day about it. Okay. Yeah, if you want to chat more about this, come on up. I'll see you guys next time. Just being admitted to the math. Okay.